Hello, everyone. Let's talk about leaving groups and protecting groups. So this is a topic of under the mechanisms tab that is kind of hard to wrap your head around, but I'm gonna do my best to break it down as simply as succinctly as possible. And please feel free to pause the video if you're confused, and or come find me whenever you need help. So let's start with the classic dilemma of something that you learned in 8A, right? Let's say, for example, you have this starting material, this little alcohol, and you want to, do this. You want to make BR, right? And the question is, right, in what you were taught in 8A, right, this reaction shouldn't be possible, right? It's near impossible, at least. Why? Because OH is not a good leaving group, right? Not a good leaving group. This is just straight up impossible. You can't do that, right? And so what do, right? Well, you've learned, right? I'm going to move everything else here down a little bit. But you've learned that roughly you can make things a good leaving group, right? By utilizing certain types of reagents, right? So instead, you might want to do this instead, right? You want to do HBr, right? So that you can have an intermediate, right? Where you get this, right? You get this little H2O right here, right? And then after that, right? Intermediate, right? And then after that, you do the reaction with Br, and then eventually you get this, and you get H2O on the side, right? Now, there's other ways that you can do it, right? That are honestly more applicable in the world of chemistry, right? And that is with tosyls, mesylates, and triflates. The whole point, right, is to do and alleviate this dilemma, right? To make OH a good leaving group. Now, essentially, right, these are different types of leaving groups you can use, right? TSCl, mesyl, right, trifle, and the ones that I usually use, right, I have a preference for tosyl, but the logic and is going to be essentially the same. So let's say, for example, right, I want to create this in the end, right? I want to create uh, BR, right, at the end here, right? So I know that, right, if I want to use one of these groups over here, right, to make OH a good leaving group, I got to choose one of these, right? And so let's say, right, well, I'm going to roll with tosyl, right? Tosyl chloride. What's going to happen, right, is that you're going to then make this group right here, right? With the addition of this little pyridine base right here. Whoops, sorry. This little pyridine base right here, right? You're going to make this OTS right here. And the Cl is going to be chilling on its side. And then once that's there, right? Now this OH, right? That has OTS on it, right? Is now able to go and be conduct an SN2 attack, right? And then from there, right? This OTS, right, will pop off. You end up with OTS over here. OTS over here, and then plus Cl. Yep. And you end up with this at the end, right? And so the mechanism for it is relatively simple, right? If I drew out OTS right here, what's going to happen is that you're going to have the OH here, right? You're going to have that OH. Going to attack right here. It's going to pop off in response. And from here, you end up with this right here. And just like the mechanism for just like the mechanism for chlorination, right? This O is going to stomp down back here. It's going to pop back off. Then you're going to end up with this right here. Entire part right here is OTS. There's, oh, sorry, TS. And this is basically that, right? And then from here, just a simple KBr, right? BR pops off, moves into attack here. This pops off, and you end up with your end product right here, right? And it's basically the same for all these other ones as well. And so you're gonna have Cl, right? I mean, this one it's basically the same structure, right? You have the sulfur, two oxygens, and a Cl, right? And you have CH3 here, you have CF3 here. Good times, right? So yeah, that is basically it there. And so we're going to move on to the next topic that we have at hand here. Let's say, for example, right, that I want to create this structure right here, right? I want to do some chlorination, SOCl2, right? Oh my God, I don't have the purple on me. I'm always running out of colors when I want to. SL2, right? And I want to go from here to here, and I propose this synthesis. Now, does this work? I mean, possibly, yeah. Let's say, for example, this was like some sort of cancer drug, right? Yeah, obviously, everybody hates cancer. It would be great if we cured it sometime soon. Let's say this is some sort of cancer drug or something, right? And so I say that, oh yeah, I can do this whole thing in one step, and I can make this drug. Well, actually, right? There's no guarantee, right, that this will happen, that you'll get this if you add SOCl2 to the starting material. Why is that the case, right? Well, there's two viable targets that you can attack, right? So you can end up with possibly, right? You can end up with this product as well, right? You can end up with this Cl on this side as well, right? You could end up there. Now, that's not something that you want to do, right? Because the drug only works if it's in this, right? And stereochemistry and the structure of the molecule is very, very important, especially when it comes to life-saving drugs. Best case scenario, this drug is ineffective. Worst case scenario, that you accidentally kill someone's grandma, right? And so let's try to do that, right? And so how do we, right, take this OH, or how do we take, sorry, this OH right here? How do we take that OH offline and basically put it in timeout and stop it from reacting so that we force this SlCO2 to attack this OH right here? Well, the answer to that is using protecting groups, right? And so protecting groups are going to be basically the exact same, very, very similar mechanism as the leaving groups, right? But essentially, right, you can deploy them in order to protect and kind of time out certain groups, right, to force a reaction to happen in a certain way, right? So how would I do this reaction if I had these protecting groups on hand, right? So let me go ahead and just kind of take this down here. I'm going to move it over here, right? And the pattern for this, right, is that while most of these, right, offer some pretty good protection, right, the major pattern that you want to know, right, is that increasing bulkiness, right, means the more stuff that's attached to it, right, means increased protection. That makes sense, right? If you had a shield, right, if you had a shield, the bigger the shield is, the more you are protected from, anybody trying to mess with you, right? Same vibe here, right? The protection of certain groups, right, is going to be increasing, right? All the way up to the most bulky group that we've been exposed to, at least. I don't know what the name of this is. IPR3 SICL, right? As you can see here, right, it has a bunch of isopropyl groups on it. Very, very bulky, as in compared to just TMSL. But any group, any protecting group in this scenario will do, right? So there's got to be, right, an intermediate in between, right, where we take a step to protect it. And so let me just triple check everything here on my end, make sure that it's all good here, right? Okay, right. So, what's going to happen, right, is that I'm going to choose a protecting group. I'm just going to choose TMSL, right? So I'll throw this in with TMSCL here. Mhm. And I'm just going to choose this group. I'm going to choose that group. It doesn't really matter in this case, right? And then this will have OTMS. Now I'm gonna quickly just move this way, right? We can't immediately go and react and make OSCL, right? Because then now, right, what we can do is that you can. Oh, I apologize. Sorry, I applied this onto the wrong group. My bad. Sorry. This is the group I want to take out, so it doesn't react. OTMS. Mhm. Then from here, right? Now we'll apply SOCl2. Then you'll end up with this TMS, right? And then you have finally have that OTMS right here. Mhm. And then from here to here, right? Eventually you can't keep that protecting group on there. And so eventually the thing that you're going to be using to kind of rip off that protecting group finally is going to be F, let's see here. Yeah, F, sorry, BU4F. BU4 B, sorry, the four too big. BU4 and F. Yep. And the last thing that we're going to talk about today, right? Hopefully this kind of makes sense to you that we want to put on a, oh, let me just correct this here. We had this originally, right? Then we move, right? Put TMS on it. And then from there, right, we're able to SOCL2, right? Put a CL onto this, right? And then you are chilling there. Okay, cool. Right. Apologies for the little errors and whatnot, but this is kind of like one of the more complicated topics, I would say. And so to kind of go over the mechanism of deprotection, right? Let me just quickly just kind of draw this down here. Let me draw a zoomed in version of it, right? Right. So let's say, for example, I had this, right? Just a random one that had OTMS on it. OTMS on this, right? And so let's say, for example, I wanted to deprotect this, right? So let me just kind of draw this all the way. Let me just kind of enlarge in this to here. O SI CH3 CH3 CH3. The mechanism, right, of deprotecting, which is this step right here, right, is that you are going to first take an F minus. F minus is going to go in, attack here. Then from there, you're going to end up with the step right here. Silicon's going to be negatively charged here. And then essentially, right, this is just going to pop off on its own. Right? And then from here, right, usually because the deprotecting, right, the BU4NF, right, is usually has water on its own, right? So it'll just kind of go do a quick proton transfer. And from here, you end up with this. Yep, all deprotected. Okay, that was protecting groups and making OH a good leaving group. Hope you all are studying hard, and I will catch you guys later. Please find me if you have any other questions. See you around.